We all switch things on and off hundreds of times a day without ever thinking about it. But actually switches are interesting things. And this video is about my experience of using them over the years on my machines. So here's the chapter list in case you want to jump to a particular section. Most people remember the very basic school experiment where you have a battery, a light bulb and a switch, and you switch the switch on and it completes the circuit and allows the electricity to flow. Some people even remember the second part of this. It's the two-way switch, so that the switch at the bottom or the one at the top can switch the light on and off. So there's the one at the bottom, and then if you switch the one at the top, that will switch it off again. If you then want to switch it on from the top, you can of course do the same thing, but you can equally switch the one at the bottom. If I switch a higher load, particularly a motor, it behaves a bit differently. You can see the switch sparks. So electricity is the flow of electrons, and this can cause air molecules to gain or lose electrons and become electrically charged or ionized. And when it's ionized like this, it can conduct electricity. So that's what lightning is. It's a column of charged ionized air. It's the same with the switch contacts. When the switch is about to make, or just after it breaks, electricity is continuing to flow through this ionized air, and that's making the contact spark. So for switching really high voltages, arcing is a very big problem and quite spectacular. This is the contact after switching the motor on and off a few times. It wouldn't be long before it stopped working at all, or actually more likely it gets permanently welded to the switch arm. I've had that happen quite a few times. The most common way to reduce arcing is to make the contacts move quickly, so that they come together quickly and they part quickly. And this is the click you hear when you make a switch. So if you take like an ordinary wall switch, when you move it, for the first half, nothing's happening at all. The contacts are still making, but you get to a certain point, just over halfway, and it goes click. And that is when the contacts suddenly snap apart. Same in the other direction. And it's just that moment when the contacts are moving rapidly. Well, it's rather difficult to see inside a wall switch, but fortunately I happen to have an enormous model of an industrial switch, a micro switch. It's a model of one of these little switches, and this is the actuator button on the top, which is here. So when you switch the switch, it moves the contacts from one side to the other. So if I go slowly, you can see the contacts stay in the same position until they get to a critical point, and then they suddenly move across. So the contact's actually pivoted here, and it's held in place by this great big spring, which is keeping it up against the this contact at the moment. But as the spring moves past the pivot, that is the moment when it gets unstable and suddenly switches. So yes, more about micro switches later. So most switches have some sort of mechanism like this to make the switching rapid. I'm not quite sure why these big switches move so slowly. You'd think it'd be more sense for them to spring apart, but they never do. So another way of reducing the arc is to add a capacitor and a resistor across the contacts, sometimes called a suppressor. I can solder my capacitor in here and my resistor in there, join them together, and we can now try starting up the motor again. Well, as you can see, it didn't make a huge amount of difference. I've never had a great deal of luck with these. You can actually buy more sophisticated ones, components specifically made as arc suppressors. You can also put a diode across the motor that sort of suppresses back EMF and stuff. But usually if I do have problems with a switch arcing, I just get a bigger switch rather than mess around with these things. Switch ratings get quite complicated, all these figures on the side. Inductive loads, ones that involve electromagnetism, they generally have a lower rating than resistive loads, and DC, if it's mentioned at all, is much lower than AC. Some switches just firmly say AC only. This one does give ratings for both AC and DC, but it's 15 amps, 250 volts AC, but only 0.3 amps at 250 volts DC, a lot less. I mean, they still work at DC, but they're just obviously not going to last so long. If all else fails, the ultimate solution really is to use a solid state switch, or rather a solid state relay. These have a control side and an output side. So you use an ordinary switch to switch the control side, and then your load, your motor, goes on the output side. And this avoids the arcing problem completely. These come in different currents, and the ones for AC, alternating current, tend to be cheaper than the DC ones. This one is rated at 10 amps at 60 volts, and that was about 30 quid, I think. Although it's useful to have an awareness of arcing and switch design, of course in my arcade machines most of the switches are just inputs into a programmable logic controller, so they're actually switching extremely low currents, and it's not much of an issue.
Lots of stars live in this Beverly Hills mansion. To find out what they're up to, use the drone to fly in close.
What'll it be, madam? The usual?
Well, hello. Aren't you forgetting something?
How could I forget?
Well, that's perfect.
Pure silver has a particularly low contact resistance. This makes possible homemade low current switches, like in my Celeb machine. When the drone crashes into a building at any angle, there's a little ring of silver in the top here, and that makes contact with the brass. But the drone can also get caught under one of these ledges, and needs to have something to detect if it gets caught above or below. And that's another ring of silver at the back here, making contact with the two brass bolts. So the switches I use come in many different sorts. There are various types of push button switch, sort of semi-industrial, miniature ones. These are ones off an arcade game. These ones actually have a little micro switch in the base of them, and they've got a light inside. or fully industrial ones like this. I was pleased to find this one because this has exactly the same mechanism as the giant micro switch for making that instantaneous contact. It's kind of them to put some clear perspex over the top. You can see it working. Sort of switch is a foot switch. Simple devices really. Foot plate there, and inside there's quite often just an ordinary micro switch. Well, this is a large micro switch with a roller on the bottom. Well, I don't usually use these on my machines. I don't think I've used any, but they're great in the workshop. I have one on my scroll saw, and it means you can keep both hands on the bit of work. Particularly good for sharp corners, so you can slow the thing right down as you turn the work. I've also got one on the drill press, which does reverse as well. Because again, it's useful to have two hands on the bit of work. So then there are rotary switches. They're good because they can have many different positions. This one's got 4. This one has got lots and lots and lots. And I use these ones with lots of positions as inputs to my PLC for testing individual outputs. Sometimes when I'm short of inputs, it's useful that you can get these switches that encode the output as binaries. So this one's only got 4 outputs, the purple wires. So I connected them to one of my logic controllers here. That's what. 2, 3, 4, 5. This is the binary encoding of the different numbers on the inputs. And of course it's then very easy for the logic controller to decode them back into the original 16 switch positions. Then there are rocker switches, though I have to admit I don't use them often. Purely because to use them you have to cut a rectangular hole, and that takes longer than drilling a round hole. So I'm much more likely to use rotary switches or toggle switches. So toggle switches, they come in different sizes. I use the little ones inside my machines as test switches for different parts of the machines. The big ones, they're good for switching large loads, so if I've got to switch a biggish motor on and off, I'll usually use one of these. And you can buy these as double pole switches, so there's 2 sets of contacts, two-way switches there. So yeah, I quite often use toggle switches as reversing switches for DC motors. So if you connect them up like this, the power supply is coming in here, and this is a center off one, so that there's it's not doing anything at the moment. If I push it up, it'll be connecting black to black. If I switch it this way, it'll be connecting black to red, and vice versa on the other side. So it's actually switching the polarity of the current getting to the motor. The switches that I use more than any other are micro switches. Wonderful things. So I have a big drawer full, and I'm going to look at those in rather more detail than the other switches. So the most obvious division between micro switches, different sorts, are the different sorts of arms they have. So the very basic one is just a button on the top to actuate. Then you can get ones with a lever arm to push the button. There's the black button just under, it's a bit hidden there. Then you can get ones with rollers on the end of the arms. And then you can get these low torque ones which they move a bit further, and they're the actuators on the side of the switch. Well, another difference between micro switches is how hard you have to push on them. So now I'm now going to see how much weight I need to okay, so it's 100 grams. This one's about 150 grams to make it switch. Another thing that can be important is how much over travel they've got. So after it switches, how much further can it go? Okay, well now I'll try it with a different switch so you can see how they vary. So this one is a much lighter touch. So that one is just 30. Okay, so this is my stiff micro switch. Okay, it switched at 540 grams. Huge difference from the lightweight one at 30 grams. So this is a low torque micro switch. Yeah, 10 grams. So that's pretty impressive really. Now the only thing about the low torque micro switch is that if I push this back to the beginning, it probably won't go off. There's actually quite a big difference in position between it switching on and switching off. And that's another thing that can be awkward in some situations. All this sort of detail about micro switches is in their data sheets. If you look at a micro switch in an online catalogue, there's usually a link to the data sheet if you need to find this sort of information. The coin acceptors on some of my older machines use these low torque micro switches. So what happens inside is that the coin goes in there, it rolls down this slope, and if the coin is too large or too small, it falls off and comes out the reject slot. Or if it's too thick or if it's too thin. So if it passes, it gets past there and then it falls down and past the switch, triggering it. So you can see inside, the other side, that's the lever arm of the switch. So the coin rolls down here past the switch. Well, until really quite recently I was having this problem with the acceptors occasionally not registering coins, and I just couldn't work out what could be wrong. They're quite simple devices really. And I'm ashamed of myself how long it took me to find that what was going on was that something had changed in the switch. I'm still not really quite sure what, but it was only triggering just on the very edge of where the coin was about to pass through. So if the coin came through at a slight angle, it was possible, it just didn't trick the switch at all. But of course, Test Your Nerve has been used about 350,000 times, so perhaps it's not surprising the switches have bent a bit. So inside my machines I use a lot of micro switches as limit switches. So they're things that move round or things that move up and down, and the machine needs to know when it reaches the end of the travel. I've just made up this model, which is a belt drive, so running a draw slide here, and you can have switches anywhere along the length. There's just one there, so it could, and this will then send the contact to the PLC, my logic controller or computer, and that will turn the motor off or activate some other aspect. Then you also need these switches at the ends of the travel to make sure it stops. Well, actually, I don't like mounting the switches like that, because every now and then I get the software wrong and it carries on and crushes the switch. It's much better to put them like the one at this end. So now it could carry on travelling if I make a mistake with the software. Present anything you like to the art expert and he'll decide if it's art or not. So the hatch goes up and down on a chain drive, and there are 3 position switches here. So if I just get it going, it's now gone down to the bottom switch. There's a sensor here that senses my hands going in, and now I have to push the other switch, and now you can see the going past that switch and go all the way up to the top to this one. And of course the motor that's making him lean over, that also has limit switches at both ends of the motor's travel. But there's another way of using micro switches as limit switches, which I use quite a lot. And for that, you connect a diode in series with the micro switch. Actually in the motor circuit, not just as an input to the PLC. And it's normally closed contact, so they're making contact at the moment. So the motor will drive until it reaches the switch. Now it won't drive back the other way because the circuit is broken. But if you do the same at the other end with the second micro switch, which I'll do now, putting the diode in the other way round, and you put this circuit confusingly in parallel with the other micro switch. Diodes only let current flow in one direction, so at any time the electricity can only flow through one of the 2 limit switches. Now the motor should run all the way back until it reaches the other one. Okay. And so if I go back to the first one, that will stop again. And then there's no way that it would overrun the micro switches. I use this a lot. The only disadvantage is that then the microcontroller, the computer, doesn't know when it's reached the end of its travel. So I sometimes end up with 2 switches at the end, one to tell the computer and one on this diode circuit to provide a surefire way of stopping it. Oh, and I forgot, the diodes have to be rated for the current that the motor circuit is carrying. Micro switches do take up a significant amount of space, particularly with the spade terminals to put them on the back. So in machines like Celeb, where I'm tight for space, I use sub-miniature micro switches. I've got quite a collection of these, these are the basic types. So that's an ordinary micro switch, and so these are about half the size. These are a bit smaller, and these are the smallest ones still. These really tiny ones are designed really for mounting to circuit boards. They don't have any fixing holes, but they're brilliant if you are tight for space. Oh, the other thing about these sub-miniature ones is that they don't carry the same current. These ones will take 15 amps at 240 volts AC. These are usually 5 amps or sometimes only 1 amp for the really tiny ones. So I also use micro switches for the control switches on the outside of the machine, but there the problems are very different. Really the micro switch itself is the least important part. The knob or lever just has to be incredibly robust. On Pirate Practice you have to bounce up and down to race your boat to storm the super yacht. So on Pirate Practice, the steering wheels, what happens with this one is that occasionally the boats get jammed, and then what people do is they really hammer the steering wheels. So the important thing is to make the stops on anything that's going to be used by the public really, really strong. I've had to re-weld them several times, so now they're a real mess. So you have to start off with really good bearings. This shell's just got some 12mm ball races inside. I usually use 12mm shaft, and that's pretty solid. The next thing you need really, really solid end stops. Now these wouldn't actually be quite strong enough. I would have to at least bolt those bits of metal through with 2 bolts on each one. So that's what you need to start off with. So then the next thing is I often want the lever or the control knob to stay in the middle center position, and I find this mechanism quite useful for that. So it's just a bit of tooth belt really. The opposite of that, I sometimes want the switch to go from one side to the other, and that's actually rather more like the contact of the micro switch. You want something that overbalances, if you like. So then if you arrange a spring like this, when it gets to the halfway point, it'll then flick across to the other side. So it's really only when you've sorted all that out that you then think about the actual switches, the micro switches, and that in a way is really the simplest part of the whole thing, just adding the switches that in this case being pushed by the 6mm bolt. Of course there are also switches like reed switches and tilt switches, but I felt that they would probably fit better with a forthcoming episode I'm going to do about sensors, so I'm missing them out. I'm going to end with one of my favourite sorts of switch, the Mercury switch. They're sadly obsolete now because of the mercury, or mercury vapour is toxic and it's a problem in the environment, so they're no longer made. But you know, liquid metal, it's just lovely. What exciting stuff. And you can actually see the contact being made. If this one's connected, let's oops. You can actually see the arc as it makes contact. So the video seems to have come full circle, back to arcing again where it started. I've got some Mercury switches in my workshop that just hang on the wall as decoration. I found them in a scrapyard. And the strange thing about them, I can't imagine why they were done like this. This is just an ordinary wall switch for 2 sockets. Why anybody would do that, I can't imagine. But it's nice to look at, and so I keep it. Well, I hope you've learnt something useful from this video. I'm going to leave you with a clock I made 35 years ago, which uses one of these mercury switches as part of the winding mechanism.